everyone. Welcome to another interview of a series of interviews conducted by the Department of Chemistry, University of Colombo. I'm Jani Marvella, a fourth-year chemistry special student, and today I'll be interviewing Prof.Laura Gagliardi from the Department of Chemistry, University of Chicago. She is the Richard and Kathy Leventhal Professor in the Department of Chemistry, the Pritzker School of Molecular Engineering, and the James Franck Institute. Professor Gagliardi became an assistant professor at the University of Palermo in 2002, and in 2005 she became an associate professor at the University of Geneva in Switzerland. She joined the University of Minnesota as a professor of chemistry in 2009 and was appointed as Distinguished McKnight University Professor in 2014. She was awarded the McKnight Presidential Endowed Chair in 2018. She has also been serving as the director of DOE-funded Energy Frontier Research Center called Inorganomically Catalyst Design Center since 2014. Professor, thank you very much for giving us your valuable time to take part in this interview. To start with the interview, could you please describe how your early years inspired you to become a scientist and what made you passionate to pursue your work in the field of chemistry?
Thank you very much, Yahani, for giving me the opportunity to participate to this interview. I feel very honored, and I'm very pleased to be with you today. So I was born and raised in Italy, and I had my education there. And I could say that from early on, I was very interested in math, physics, science, and I don't know if one of the reasons was because my mother was a math teacher in high school. Now she's retired. And so seeing her as my role model has always inspired me. But also I really enjoyed the aspect of problem solving that is associated with the scientific disciplines. So I was fascinated. But then, in Italy, when you go to high school, you can choose different directions. And actually, I went to a so-called high school where you do classical studies, and I studied Latin and ancient Greek. So it was more heavy on languages, all languages, rather than science. But still, I thought also actually studying Latin and ancient Greek had that rigor that I also found in mathematical sciences. So I really was curious about everything in school. I liked all topics, but I thought that the logic, the way of approaching problems that you have in science was more exciting for me. So and then when it was time in Europe, it's different compared to the US. In the US, when you go to college, you can study a little bit of everything, and then you decide what to major later on. While in Italy, in Europe, you have to choose a topic from the beginning of college. So when it was time to choose, I had to choose either math, either physics or chemistry. And I decided to choose chemistry for a series of reasons, maybe very practical reasons, probably because I thought it's easier to find a job if I am a chemist, rather in those years, especially chemistry was blossoming. And so I studied chemistry. And I enjoyed a lot, but along the way I realized that I was more interested in physical chemistry rather than perhaps organic chemistry. So I really like to try to understand why certain phenomena occurred. So rather than making things, I was more interested in understanding why things worked in a certain way. And so physical chemistry in this respect was really very fascinating. And especially when I started studying quantum mechanics, it took a while to figure out what was going on, but finally when I got it, I was so excited. And so that's how, and I think that, so actually as an undergraduate, I did a research project. It was in spectroscopy, so it was in the lab. And of course, I really liked this aspect of understanding what was going on. But then I thought that, yes, the theoretical aspect was so exciting for me that I decided to do a PhD in theoretical chemistry. So that's how it all started.
Professor, could you explain me briefly about the type of research work you are doing at this moment?
Yes, so I mean, I am, as a background, I did my PhD, it all started there in electronic structure theory, in particular in configuration interaction methods. And at that time, I really studied very small molecules. Like, I remember one of the molecules that I studied in my PhD thesis was a boron hydride, 2 atoms. And nowadays, I mean, over the course of my career, I think I've moved more and more towards more extended systems, switching a little bit from molecules to more materials. But there is a unifying theme, and I say that nowadays we study, in my group, we study materials and chemical systems related to what I like to call sustainable energies. So problems related to catalysis, to heavy elements, to separations. And we use electronic structure theories. And for some of these systems, the methods that are well established, that one can take out of a shelf, are not working because the problems are so complex. Let's suppose that you want to study magnetism of a molecular crystal. You have to study, for example, all the magnetic behavior of the individual molecules that form the crystal, but also the interaction between the environment and the molecules, so the spin-phonon interaction. So the methods that are there, maybe they can do part of the job, but not all of it. So we develop also electronic structure theories. And in particular, I think that one of the big challenges of our modern community is to study strongly correlated systems, where for strongly correlated, I mean that there are many electronic configurations that are all important, and they have all to be taken into account when describing these systems. And so I like to think that I want to use, even when we study these more extended systems with more complex systems, the same level of rigor that I learned when I studied boron hydride, this small diatomic. And of course, the methods that one uses for these small systems cannot be used like that in a similar fashion for the extended systems. So one of our big challenges and goals in my group is to develop methods for strongly correlated systems, but are affordable for these extended materials.
So, Professor, what are the major discoveries you came across through your research activities, and out of them, which one do you think has the greatest impact on the scientific community?
So I think maybe about 15 years ago, I had a moment of celebrity related to our study on the uranium dimer, so U2 molecule. And what was very interesting about this molecule is that first of all, the electronic structure is very complex because there are many electrons, so the F electrons, but also the D, P, and S orbitals may participate there. So one has to compute any electronic state. So it's a very dense spectrum, and the spin orbit coupling, relativistic effects have to be included in the treatment. So it was a very intense calculation, especially in those days. But what really the concept that we introduced was that between these two uranium atoms, there is a multiple bond, and we defined it as a quintuple bond. So also that work allowed us to talk about high bond orders in diatomics in the periodic tables, and we looked also at transition metals, and we looked at the tungsten dimer, which has a hextuple bond, which is probably supposed to be the highest bond in the periodic table between two atoms in a diatomic, in a covalent bond. And so that was, I think, was a important work that inspired future work, also experimentalists in making inorganic compounds with a central metal-metal multiple bond. And I think that work has been followed a lot. There has been another paper last year, again on uranium-2, a theoretical paper. It was revisited by some groups in Europe, Stefan Hecht and Tronsauer, and basically they used a more advanced relativistic treatment than the one that we could afford in 2005, and they showed that the ground state of the molecule is a slightly different one compared to the one that we predicted, and according to their prediction, the bond is only quadruple, not quintuple. But I mean, seeing that this work is revisited also 15 years later was very interesting. And as I told you, more recently, I've moved more to more extended materials. So in the last, I would say, 5-6 years, I've been working a lot on metal organic frameworks, which are these hybrid species containing an inorganic component and an organic one, and then one forms these reticular structures with high internal surface area that can be functionalized for various applications. And I think we really made progress in, first of all, studying the adsorption properties of these materials for example, carbon capture by combining, we have developed force fields from first principle calculations. So combining quantum mechanics with classical mechanics has been very impactful, and we had this paper in combination with a person who does more classical simulations, Baron Smith, in 2012, called ab initio carbon capture, that I think has been recognized by the community. More recently, we are interested also in more, I'd say, catalysis process on these MOFs. So in terms of applications, I would say that these are some of my fingerprints. In terms of methods, we have always been interested in multi-configurational methods. And I think my group and I have pushed really the potential of these approaches beyond their limits, because these methods originally were intended for small systems because they are quite expensive. So we have introduced a way to make the scaling of the wave functions less heavy, less not exponential, but reduced. And so these methods nowadays can be used also for really real-world applications. I would also like to say that I mean, I've been very lucky over my career to work on exciting projects, but my work has always been possible also because I had wonderful collaborators over the years. Not just my group, of course. I'm just here, I'm the face of my group. They are the real people who do the research. I just speak. But also I had, along my career, really inspirational mentors. And so my interest for multi-configurational methods and this metal multiple bonds has certainly been inspired by working with the late Bjorn Roos from Lund University, who was one of the pioneers in multi-reference methods. And also I've started being interested in actinides, so uranium and other actinides, as a postdoc when I was working in Cambridge with Nick Handy. And so this has been also very inspirational. And also there, I learned a little bit about that. So with Nick Handy in those years, he was very interested in density functional theory. So I was actually working on density functional theory. I wrote a code, but I talked both with Nick Handy and Bjorn Roos, and I saw the two different worlds, the DFT world, the multi-configurational world. And one of my goals has always been to try to combine these two words. And this is actually something that I've realized more recently in my career. So starting in 2014, I've been working on a method called multi-configuration pair density functional theory, which is really a combination of the two words. And this has also been a collaboration with my colleague at Minnesota, Don Trular. And I think this is also a very exciting project. So overall, I've been working in a combination of methods and applications. And I think they have inspired each other, because when we wanted to study a really challenging problem, we didn't have the methods, so we had to develop them. At the same time, when we developed a method, then we tried to find a really challenging application for that method.
Professor, there could be ups and downs when conducting research work, and also especially during the process of publication of novel research findings. So how do you overcome these hardships, and what helps you face challenges and strive forward in the field of research?
So, I mean, it's true that sometimes the project doesn't work in the smooth way that you like it to work, or sometimes you have a nice project that in your opinion is working well, and then you write a paper, and then the paper doesn't get accepted as soon as you'd like it to. So I mean, my idea is that I always want to do exciting science, at least that I think is exciting for me, and I want to do it in a very rigorous way. So what we do has to be correct. Of course, it doesn't mean that it has to give the right answer, because sometimes we use approximate methods or models, but everything has to be done in a very proper, rigorous, ethical way. So when I think we achieve this goal, so we are working on something that we think is very exciting, we do everything really properly. Of course, sometimes things don't work, but the point is that as a scientist, if you encounter a difficulty, your goal is to overcome it, and finding difficulties along the way may help you to find a better scientific solution, or address a more exciting problem. So my suggestion is just always try to follow your rigor, your passion, and ask yourself always what is the next step, what is the problem here. So I say always to my students, remember, as a researcher, you're not like going to class in which you are told, study this book, this chapter, do this exercise. It's you are free to explore the universe with your own means, but always ask yourself challenging questions. Always try to see, okay, I've obtained these results, but what are the problems of these results? What are the implications of these results? So that will allow you to go one step further. And of course, when you write a paper, of course, I'm more mature than I was 20 years ago, and I see things slightly different. But as a reviewer, I am a reviewer many times, and my goal as a reviewer is not to kill anything, because every scientific product has some dignity and has the right to be shared with the community. But how can you make it better? How can you present it in a better way? So when I receive referee reports, even if there is criticism, I try to say to myself, if I follow the suggestions of the reviewer, I will, my idea will advance in a more complete way. I will write a better paper. So this is very important. The other thing that I think is very important, and again, it's something that one acquires with experience, is communication. It's very important. I tell it to my students, maybe you have really discovered something that deserves a Nobel Prize, but if you cannot communicate it in a clear way, in a convincing way, nobody cares. So try always to have the ideas clear in your head and communicate them in an effective way.
Chemistry is known to be an interdisciplinary subject. So, how have your research findings influenced other fields in the science like biochemistry, biophysics, and molecular biology?
So my research is more towards materials than bio. We have explored some general concepts that certainly are important also in biochemistry or molecular biology. Because, for example, we are very interested in transition metals and their environment, and so if you have a compound with a transition metal and a ligand, what the properties are, spectroscopic properties or reactivity properties. And this, of course, can happen in biochemistry, happens in biology. There can be in transition metals surrounded by a protein in the human body or in any body. And so I think that understanding really the molecular or atomic and electronic properties of these systems allows you to understand phenomena at a larger scale and also relevant in other areas.
Professor, congratulations on being awarded the Peter Debye Award in the Physical Chemistry of the American Chemistry Society this year. You are the first woman to receive this prize. You have also received many other awards like Humboldt's Research Award, Burke Award for Royal Society of Chemistry, the award in Theoretical Chemistry from the Physical Chemistry Division of American Chemical Society, etc. So what inspires you to achieve these awards, and how helpful have they been for excelling in the field of science throughout your research career?
Yeah, so I feel very lucky that I had all these recognitions, and I think probably the reason why I had them because again my science, the science that my group is doing, has shown to be rigorous, impactful, and inspirational, not just on what we are doing, but in other areas, as we discussed before. And I think that I feel very personally very happy about these achievements, but I think it's more important, not just for me, but for the society. Like I am, as you said, I'm the first woman to receive the Peter Debye Award. I hope I can be a role model for younger generation of women who you can see that they can also get in that position at some point, because it's possible for women. So that's, in my opinion, the importance of these awards, to show that society is evolving and that people can make a contribution.
In your opinion, with the current global pandemic situation, what are the necessary steps that are needed to be taken by the scientific community to adapt and overcome the hardships to bring out the research findings as before the rise of the pandemic?
So in a way, I'm lucky because my group and I, we do computational theoretical research. So we have been impacted in a minor way, in the sense that we have been able to continue our research. Of course, we had to adapt to a different situation. I've not been in an office, neither in Minnesota nor in Chicago since last March. I've always been working from home, and the same for my students and postdocs, and we meet virtually a lot, but it's not the same as an in-person meeting. So this is certainly important. Of course, the limitations for people who work in a laboratory and they do wet experiments are major, because the research cannot be conducted at the same pace as before. But I think that the other problem is the fact that we don't have the human contacts that we used to have before. So, one thing is to have a Zoom meeting with my students here. One thing is to be sitting in a room all together, and then maybe there is a more relaxed atmosphere, and then maybe some ideas are discussed and came up. So I think that the human interaction is very important. It's important for me because of my personality. I'm probably a extrovert person, so I really miss being with people. But I think it's important, especially for young people, young students. Now they are maybe in isolation, they are at home all day long, either alone or maybe they have a roommate, and the condition is not ideal to work undisturbed. So this is really bad. The other aspect is, you know, in our profession, we go to conferences, and this is something that at the moment is completely missing. And perhaps the conferences are more important for young people rather than for established people. I mean, if I go to a conference, of course, for me it's important because I meet my colleagues, maybe we discuss about ideas, and I meet the next generation. But I think for the new people it's very important. I was talking with my students who now started their second year. They have never been to a conference, and that's terrible. So talking to other people, expressing your scientific ideas is important. So this is certainly something that is damaging us. At the same time, it's resetting our society. So of course, going to conferences is important, but I wonder how many conferences, were we going to too many conferences or not? So I think we have to rethink not just our work, but the way in which humankind lives in the society is slightly different, and adapt to that. But I hope to be able to be with my group in person soon. Last summer, we met a few times in a park along the river, and just seeing them, having the feeling of being with them again was so beautiful. So,
Professor, from your point of view, what are the areas of science in general will be most promising in the future?
so not just in chemistry, you mean in general? Well, okay. So sometimes I ask myself, if I were to start it all over, what would I study? And so I mean, I think chemistry is still really very important, because you really understand how matter, how the universe works at the level of molecules and atoms. But and then one can have an impact in many other areas like medicine, biology. So I think that and we haven't discovered everything. I think will change, are changing, because, for example, whether one likes it or not, data science, machine learning will play a major role. And it doesn't mean that they will replace the human. I think the human will always have the most important role in defining directions and making choices. But it will help a lot, because having a lot of data, access to a lot of data, and being able to analyze them and find trends fast really will speed up things. So I think that combining data science and machine learning with physical sciences like chemistry or physics is very important. For me, I mean, sometimes I say, if I mean, another topic that really fascinates me a lot, and in which there has been a lot of progress, but perhaps there could be more, is understanding how the brain works. So a neural network, but neural sciences. And again, that's a discipline, it's a multiscalar discipline. One can go from really the chemical study at the molecular level towards more biology or medicine. So these are certainly fields that I think that another field that is very important is quantum information. And it's important because, I mean, the quantum computers, they now have started being developed at a more interesting level. I don't think we are anywhere close to quantum supremacy, but there is certainly fast development in that area, and we should be aware of it and exploit it. And so besides the interest that in my group we have towards quantum materials, so systems that eventually can be used to build some qubits. We are also very interested in translating our theories and our codes into quantum-ready theories, quantum-ready codes, so codes and theories for quantum computers. And I think that combining quantum information with machine learning will also allow to advance knowledge in an impactful way.
When striving for the discovery of more sustainable and renewable energy sources, it is important to follow the research in an eco-friendly manner. How is this being achieved by your group when conducting research activities?
Well, you know, we are theorists, so we are eco-friendly by, well, okay, we use computers, but for sure what we are trying to do, and again, this is a collaboration with experimentalists, focus more on more earth-abundant metals, for example, in catalysis. Instead of using noble metals, what about using first-row transition metals? So this is a way to really be more gentle towards our planet. And we try to address our computational research towards this direction. Or another aspect is, for example, solar energy. This is very important. And again, so can we address our computational studies towards solar energy related problems so that overall research science becomes more eco-friendly? And it's not just about science, it's about the sources of energy that our society uses.
It is important to educate the general public about the work that you are doing. So what are the ways by which the general public who are keen on knowing the latest scientific findings get to know about your research team's discoveries?
So, of course, we have a website in which we upload all our latest publications, and sometimes we have some little news sessions, but also I'm very active on Twitter. So usually when we have an exciting news, scientific news, I advertise it on Twitter. And of course, the more traditional way is that either my group or myself, we go to conferences and give lectures. But I think nowadays with social media, with there is a possibility of at least knowing about something right away. Of course, to understand the details, it's much better if you talk to the person, if you have a scientific meeting. But I think that the fact that one can communicate things so fast helps a lot to be on top of things.
Professor, what do you like to do when you are not working in the laboratory or outside your research work?
So here in Minnesota, I spend time with my husband, who is also a faculty, Chris Kramer. I think you are in your program, he has been interviewed as well. But we have 2 cats, so we like to spend a lot of time with our cats. I tweet also about my cats. I like to do outdoor activities or sport in general when the weather permits. I also play piano a little when I have time. I don't make enough progress. I also am very close to my family in Italy. My parents are there. I have a brother, a nephew with whom I'm very close. And so when I can, I try to visit them and we try to spend time together.
Finally, Professor, I would like to ask you, as a renowned scientist, what advice would you like to give to prospective young scientists who are planning to pursue research as their career?
Okay, so I would like, so the first thing is follow your passion. So try to figure out if you're really passionate about science, about a particular scientific topic, because day-to-day research is not always fun. I mean, it's fun to make a discovery, to achieve a good result, but it requires a lot of concentration, a lot of hard work. And as we discussed before, things don't always work out the way you'd like to. So there is some frustration. So, but if you have this passion and you think that what you're doing is the best thing in the world, then you will always find the energy to do this. So this is certainly important. Of course, one is to understand that one is to learn a lot, and so always be humble. And the more you learn, realize that the less you know, because there is so much to learn. I think that it's also very important to establish a good relationship with other people in your work environment, but not just polite, not just polite, but really support each other, both emotionally as human beings, but also scientifically. And in my personal experience, I've learned that collaborations are really very important to advance science rather than competition. So be collaborative with your peers and understand that maybe sometimes you have to share a little bit of your findings, but you will get something back from that. So be a good human being at work, and don't see it as a fight in which one is to be superior to the others.
Before concluding this interview, I'd like to thank Professor Laura Gagliardi for joining with us to share her wonderful experience in the field of chemistry and research. I believe this interview will inspire young scientists and students who are planning to pursue further in the field of chemistry. That concludes today's interview with Professor Laura Gagliardi from the Department of Chemistry, University of Chicago. Thank you everyone for joining with us. Have a great day.
Thank you so much. It was a pleasure, and I wish you all the best in your career and a lot of success to you and the other people in your program.
Thank you, Professor.
Thank you.